Hey guys, so today we're going to be covering context switching. So I'm just going to go over the agenda real quick. So we're going to start off by covering what the hell a context switch actually is, how it works on a simple basis, how it works in more detail, and then what context switching actually implies, how it will affect the OS, how it will affect the system, how we can minimize these implications as well. Okay. So, what is a context switch? A context switch is defined as switching the process currently on the CPU. This is by saving the current process onto the stack and all the information related with it when we finish with a process or a time slice for a certain process or when interrupted by the OS, which refers to limited directed execution. Now, I don't think limited directed execution was actually covered within the actual slide, so I'll just give you a quick brief about it. So, whenever we have the OS, we have these programs running, right? Now, they can't all run in the. You can't have a program constantly running and not yield control back to the OS. So, limited directed execution is a way in which we have timer interrupts. So, there's like these timers, and they will cause interrupts to the system such that we can yield control back to the OS, so that the OS can pick up on things such as malicious or error-prone programs and terminate them, rather than having programs just run by themselves. So these interrupts are one of the reasons that can cause certain processes to pause. You can also have another reason, such as having a system call. You should be able to see this diagram over here. So you can see, for example, we're on process P1, and when an interrupt or a system call happens, we save the state into the PCB, so the process control block that just contains all your information, and we reload the state from the PCB2, which relates to process P2, right? And so then we know that our process P2 can execute, and then after the interrupt or system call, we just do the same thing, but in the opposite way, such that we want to run P1 again. So we'll save the state of the process 2 into the PCB, and we will reload the state from PCB1 in order to start running P1 again. Cool. So this is basically the simplistic context switch. I've basically explained it, but I'll go over it again. So here we're looking specifically at the example of a process yielding to the OS due to a time slice finishing. I think the slides will refer to this as a time quantum. So a time slice is basically just the time that a certain process has been allocated to run on the CPU for. So we'll start off. So firstly, obviously, like we said before, a timer interrupt will happen, which will cause the process to yield to the OS, which is known as preemption. Um, I think it might have been covered within processes, so you can have a look at that video as well. So preemption just basically means removing the process from the CPU into the ready queue. So the process state in the process table will change from running to ready. After that, we save information related to the process and select the next process. So specifically, we save the context of the process. You can also save the context of a thread as well. So you have a PCB process control block, which is where we store the context of a process. But for threads also, you can have what's called a TCB or a thread control block. So that's just the same thing, but for a thread. Obviously, one thing to note is that when context switching, you context switch between several processes, right? And those will all have different memory allocations. But the TCB, right, when we refer to switching between threads, obviously each thread within a process, right? They all share the same memory space, right? They share that one memory allocation. and so that heap is shared between those threads. The only thing that isn't shared between those threads is a stack for all the instructions, or like stack frames when running functions, right? Cool. And then yeah, we select the next ready process to run. This, I'll go into more detail on the next slide, but this is usually done by the scheduler. I won't go through this much information today in regards to the scheduler. We actually have another session that will be covering schedulers and scheduling tomorrow. But I'll give you a brief overview on the next slide. And then we load the new process into the CPU. So we load this new process into memory and we flush the TLB. The TLB is just a translation look-aside buffer, which will basically cache pages. So we cache these pages in order to improve the performance when doing paging. So this is because paging is usually done within memory, within the RAM, but cache is obviously quicker, right? As it's closer to the CPU. And because of this, we can store more frequently used pages within the TLB to minimize the amount of time it takes to actually get a page. Instead of having to like go to a page table, you can look at the cache. Cool. Now the reason why we actually flush this TLB, if needed, is essentially whenever you load a new process, obviously you won't be looking at the old process information, right? You'd be looking at the new process information. And if we want to have like a cache of the current process in order to speed up our paging, then we need to remove all the previous process related things. And because of that, we will flush the TLB. I'm going to go into a bit more detail about this on the next slide as well. Okay. And then once we finish, we can then restore the context of the original process back from the stack and the PCB or TCB. So yeah, that's basically a context switch in a short form. Now I'm going to go into a bit more detail. Obviously, these slides will be available after as a recap. Cool. So one thing I will say is that not everything. Oh, we've got a question in the chat. What do you mean the original process if it's the new one? So when I'm referring back to the original process, so if we go back to this slide, right? So we have this original process P1, we context switch to P2, and then we go back to the original process P1. Cool. Okay, more complex context switch. So let's go for it. So as before, timer interrupt, which is due to a time slice ending. And then this will cause the current process to yield to the operating system. Hence our process is preempted and the process table is updated. So this process table contains information about all of these processes. They contain like the PCBs, right? So we will update the state from running to ready. So it says here where the current process is now ready and not running. Then a trap instruction is triggered. So a trap instruction is basically an instruction that will usually be associated with system calls. So whenever you do a system call, most likely you will go into kernel mode, right? So whenever you go into kernel mode, you need like a safe way to actually go into kernel mode, into this higher sort of ring level, right? Or like authentication level in a sense. These trap instructions are a safe way in order to do this. So these trap instructions have handlers within a trap table, which is just something within the kernel memory. And these are done at boot time. So these are loaded at boot time. And then after boot time, these can't be changed. So basically, it prevents like malicious attackers or error prone programs to it prevents them from actually changing anything within kernel mode, because obviously we don't want like errors or malicious code being triggered within such a high admin level, right? Obviously that being ring 0. So yeah, a trap instruction, this basically triggers us to move to kernel mode. Now the reason why we move to kernel mode is so that we can push everything to the stack. The stack that we actually use to push everything to is the kernel stack. So it causes us to context switch and enter kernel mode, and we push the state to the kernel stack as a stack frame. So a stack frame is just like one instance of like an object on the stack. Or we can push all the states of registers and other forms of storage on the CPU onto the PCB or TCB as well. Now, it depends on sort of what architecture you use. Some can be using the CPU and PCB architecture. Some can be using just stack frames. Some can be using both. I think usually nowadays it's both, but yeah, cool. So next up, our scheduler will choose the next process from the current process table, filtering out the ready state processes. So this basically, in short form, is just the ready queue. So our scheduler will choose the next process from the ready queue, while we set the current process to ready or waiting, depending on what our current process yielded control to the OS for. So yeah, it's not always just going to be like a time slice that will yield everything to the OS. It can be other reasons, such as blocking I/O computation. So, like, let's say we're using File Explorer and we wanted to open a file. Then, if we click open on that file, the process might go to an I/O operation in order to get all the data from your disk drive or your SSD, in which case your process would be set to waiting, and your process would go into the device queue, right? We then load the next process PCB and save all of its values in the current registers, memory, and PC being the program counter. So this program counter tells us about which instruction we're on. So it's good to be stored in the stack for specific programs when we run them. And if we have a page table, we will change the page table base register containing the address of the current process. Now, the page table base register is just a way for computers to track which page table we're on. Now, obviously, within paging, we can have page tables, but we can also have multi-level page tables. I'm not sure if this has also been covered, but multi-level page tables are basically nested page tables, so you can have a page table within a page table. They're also called page directories, in which I'm just going to use that in order to sort of differentiate between a page table and then like a multi-level page table. So these page directories, obviously, when we have nested page tables, essentially what happens is you can have various processes within your current like memory, within like the running programs and whatever. And usually what happens is this page directory maps a process to a page table for better control. So it's more easier to manage these processes. And so usually, in order to track which page table we're on, we have this page table base register, which stores the address of the current process. Cool. So yeah, we will then flush the translation look-aside buffer to avoid cross-process translations. So obviously, when we have processes in most computers that are modern, we will always have some sort of virtual address, right? That will map to a physical address. And sometimes within these processes, since virtual addresses are dynamically allocated or dynamically made, so they're made at like runtime or execution time, because of this, Sometimes what actually can happen is that you might have the same virtual address that's stored within either like your TLB or maybe some other cache. So we flush these caches, we remove everything and reset these caches to avoid like conflicts between them. Now, this won't actually happen when we use tag TLBs. So tag TLBs are just TLBs where within each TLB entry, we have an address space identifier. So an address space identifier is a good way to avoid cross-process translations, as instead of having to flush everything, the TLB will contain like a process identifier. So these address space identifiers usually relate to the process, because obviously a process has a memory allocation which has a specific address, right? So these tag TLBs, the they will have entries like a normal TLB, but these address space identifiers will be sort of an extra thing within that entry. And so we can use the current address space identifier for a specific process and check against the virtual address as well in order to ensure that we are looking at the unique current process virtual addresses rather than anything. So that will prevent us from having to flush the TLB. But yeah, we then restore the context of the original process when the process has ran and yielded control again, when the scheduler will then next choose the original process. Now, this obviously won't always be the case. So if we go back to the current image here, obviously it's not going to be as easy as P1 to P2 and back to P1. It's not going to always be that case. It could be such that we go to P1 to P2 to P3. It depends on the scheduler, right? It depends on how the scheduler will actually pick from the ready queue. But we enter kernel mode again in order to save the state of the process once more, and then sort of switch our context back to some other state. Let's say for this example, we are actually going to go back to the original state. We will enter kernel mode through the trap instruction, change our state, and save the state of the current process, exit kernel mode, and then we return back to user mode. So obviously a low privilege within the OS, and then we resume execution. So that's basically what a full context switch will look like. Now, there's a lot of implications of these context switches. So with respect to an OS, obviously for an OS, the main point of having an OS is so you can manage multiple processes with abstractions, right? So we abstract away all the logic and we're able to manage these processes, manage these programs and run them. And we want to be able to run them safely and also efficiently. But I think one thing when actually having an OS is there's going to be a lot of overhead, right? Like, for example, when you install, like, when you get a new laptop, right? And you have like Windows installed on there, you'll have a lot of memory on there, right? So that memory will be related to the OS, it will be related to Windows, right? And you can use that storage on Windows to actually load everything up into memory, right? And then you'll be able to run the OS. So you'll always see, like, let's say if you open Task Manager, there's not going to be like a 0 GB like Task Manager thing. Like if you go into Task Manager, it won't be such that there's like nothing running because obviously the OS is running, right? So that introduces a lot of overhead, and the OS in general introduces latency through things like context switches. So there's a lot of implications of context switching. So for example, expensive computation when switching to kernel mode. So when we switch to kernel mode, when we do this trap instruction, it is an expensive instruction, and it will cause an increase in latency. Um, Context switching will also be complex to carry out alongside all other processes because obviously it's not just a one-way thing. We're not actually doing a linear when there's no linear approach to context switching. We have concurrency within our OS. We might even also have parallelism as well. So you're managing so many different things at once. You're managing interrupts, you're managing threads, you're managing multi-processor systems, right? So to actually like for a developer to code this up is really complex in general. Um, in order to ensure safety of processes, it is very complex, and this will then usually lead to either longer task completion times or latency, and also introducing overhead memory-wise for managing these processes during a context switch. Um, and also, when we context switch, when we save the registers, when we save all the information on the CPU related to the process, when we try to switch, this can also be expensive as well. We also have something called cache pollution, which basically is when, or cache resetting. So when we reset the TLB, because obviously a TLB is a cache, right? There's obviously going to be other caches as well. Um, So these two kind of relate in a way. But when we reset or flush these TLBs or these caches, we lose all that information related to the process, right? So when we lose all that information related to the process, you then have to re-add everything back to your cache, back to your TLB, right? So let's say, for example, going back to the previous one, just to explain. So when we save the state of PC of the process P1 into the PCB1, it's not always going to be the case that the cache is going to be stored. The caches aren't usually stored within your PCB. It's only the information that's needed for your process that's going to be stored in the process control block. And so when we start like running this P2 process and we go back to this P1 process, that cache is going to be empty now. And so when you try to either sort of when you're doing something like paging or when you use a cache, that information won't be there in that cache anymore. That information or pages, when we talk about TLB, those pages won't be in the TLB anymore, and they'll lead to something that's called a compulsory cache miss. This is basically just a fancy way of saying we won't be able to reduce the time of getting a page because the page isn't within our TLB. So because of this, obviously you're going to have an increase in latency, right? So we're introducing latency because we flush our TLB or we flush our cache. Another thing to mention is scheduler complexity increases. Like I said before, when you have so many different things running in the OS, your threads, parallelism, interrupts, then there's going to be more decisions that need to be made within the scheduler, right? Especially alongside doing context switching. Because obviously we don't want to interrupt certain processes. We don't want to have that sort of we don't want to have inconsistencies when running OS programs. We don't want to have any sort of inconsistency in general when running programs within our OS because that will lead to errors, right? So in order to ensure that safety, the complexity of a scheduler will also increase. Now, how can we actually look at these implications and how can we at least minimize some of them? Now, one thing to note, some of these you can't really sort of reduce the computation of the only thing you can really do is just improve your actual hardware support. So like improving the processors, maybe getting like a better laptop, for example. And the complexity will always be there. The more modern a laptop will be, it's more likely that a laptop will have a lot of complexity related to it when carrying out these processes along in a context switch. But yeah, how do we actually minimize these implications? So, like I was saying before, you can use tagged TLBs. So this will help to prevent those TLB flushes. So we don't need to reset those TLBs, and hence we won't waste computation on flushing the cache, flushing this TLB, and we won't have to have these cache misses. So obviously, when a cache miss happens, we will then get the page from memory, right? And memory computation or memory access time is usually bigger or slower than a cache access time. So by having less flushes, we're more likely to keep our pages within our TLB, and hence because of that, we're benefiting more from the cache. You can also improve the cache affinity for processes. Cache affinity relates to a process sort of remaining on the same CPU, and when it remains on the same CPU for longer, the cache obviously remains there. There's no context switch that happens. And so when there's no context switch that happens, firstly, obviously, a cache, a context switch is generally expensive for some of the reasons mentioned before. But if we improve the cache affinity, we won't be doing firstly those context switches, and those caches, we won't be having like those compulsory cache misses. We won't have to have like information not being within the cache because we flushed it, because we've reset it. So if we improve the cache affinity for processes, we have a performance advantage for running processes, as they'll usually have better performance than processes that will move from one processor to another, right? We can also minimize the latency of the scheduler. Now, I believe so. We'll go through scheduling a little bit tomorrow, but I'll talk a little bit about like a scheduler. So you guys probably know about like priority scheduling, right? So priority scheduling is basically like getting like a priority queue. Um, so you're sorting all your processes from like lowest to highest priority, and you pick the highest priority process and run that, right? That's like one way of having a scheduler. Now, a in Linux, there's this thing called the completely fair scheduler, which is the actual scheduler that's used within Linux. Now, this sort of this scheduler uses a red-black tree, which is quite similar to an AVL tree, where you have like these log n insertions rather than having to do like a O of n like linear comparison, right? Or sorry, not comparison, but linear search, right? Um, Within your scheduler. So by improving your algorithm for the scheduler, you're obviously reducing latency in that way, and that will scale as well, because of like things like Big O, right? And hence, since the scheduler is involved within the context switch in order to pick the next process, it will directly affect the latency of the context switch, and hence minimizing the latency of the scheduler will minimize the latency of a context switch. Another thing is when doing context switches, you could have the smallest amount of time between a process running and the next process running. But then obviously, if we're going to be constantly switching from process to process to process, there's going to be a lot of context switches. But it's basically going to be excessive. So another thing that this Linux scheduler does is it has something called a minimum scheduling latency. I don't think I've written it on these slides here, but hopefully you can have a read through this on maybe I'll post something on recaps about this. But this scheduler latency is basically the minimum time slice, this minimum time quantum that we can run a process on our CPU for. So when we have various processes and we consistently switch between all of them, we don't want to have so many context switches that it's just going to be bottlenecking our CPU. So we must have some sort of balance, right? And hence, by having this minimum scheduler time slice, we can control that and minimize the number of context switches we have. Now, this will obviously be dependent on what sort of hardware you're running on, um, but yeah, this is essentially one of the ways in which we can reduce the number of context switches and hence reduce the number of, well, not the number of, but reduce the latency of the OS. Um, yeah, cool. So that's basically context switching, and hopefully we can do the scheduling stuff tomorrow. Cool, thank you.